Hello, we are a team of students from the computer engineering department and the material engineering department. Today, our team will present on the topic of automated TFT parameter extraction, which can determine electrical performance by extracting characteristic parameters based on electrical data measured from the IGGO thin film transistor that I experimentally fabricated. I will present in the order of introduction, project process, and conclusion. A thin film transistor is one of the components that make up the display screens of laptops, smartphones, TV. It controls the current flow to each pixel, thereby turning the screen on and off. A thin film refers to a film less than 1 micrometer thick, and a semiconductor device made by stacking these films is called TFT. Through a total of 20 experiments, we were able to obtain electrical data measured using a semiconductor parameter analyzer from 966 TFT devices. For the measurement, the drain current was measured according to the gate voltage change at 0.02 volt intervals for each TFT, from minus 20 volt to 40 volt. Various mathematical calculations on the measured electrical data yield four parameters: threshold voltage, saturation mobility, subthreshold swing, and on-off ratio. These parameters were used to evaluate the performance of the device. The method for calculating the four performance evaluation parameters of TFT are as follows. Subthreshold swings evaluate how quickly the device turns on and off. The on-off ratio evaluate the reliability of the device. Threshold voltage evaluate the power consumption of the device. Mobility evaluate the operating speed of the device. This performance evaluation process is very time consuming, so we tried a new approach. Most device performance evaluation process generally require the experimenter to calculate and confirm the results directly. This is a time-consuming task. However, when machine learning is applied, the direct calculation process can be omitted, significantly reducing the time required. Recently, in the field of computational materials, artificial intelligence has been used in various studies such as automatic phase recognition, fossil detection of atomic defect, and enhanced detectability in gas sensors. The overall flow of the project is as follows. Paper we selected as a reference is published in the ECS Journal in 2022. This paper focused on explaining the performance difference according to the neural network depths by selecting ANN and DNN as learning networks. We proceed in the direction of improving the performance of DNN and introducing CNN. The pre-processing proceeds as follows. Unlike the refined data obtained through ticket simulation, our data were experimentally measured and negative current values were sometimes recorded in the off-current measurement interval. These outliers were pre-processed using imputation with nearby values. First, among a total of 966 sample data points measured, we used the K-means algorithm to filter and select high-quality data for deep learning. The log-scale transfer curve was clustered into 4 levels and divided into 4 grades. Among them, medium and low-grade data were initially filtered out. However, Some detective data were mixed in with the high-quality data obtained through the first k-means clustering. Thus, a second k-means clustering was performed based on the linear scale transfer curve to filter out the blue curves. In this way, 606 filtered high-quality data points were selected as deep learning training data. The ground truth was obtained by writing and calculating the following formula through Python. Ground truth data was obtained as shown in the picture on the right. Among these, it can be seen that the scale of the on-off ratio is very large. If the learning is conducted by setting it as the target value, there is a problem where the large differences between the values result in abnormal learning outcomes. Therefore, the log transformed value was used as the target.
We initially attempt training a deep neural network (DNN) as described in the reference paper. A DNN processes data by passing it through multiple layers of neurons. Its neurons perform linear transformations and nonlinear activations. This allows the network to extract and combine complex temporal and spectral features for prediction. Here's the visualization of results in the paper. To improve upon this, we attempt to tune hyperparameters. We give parameters such as batch size and the number of layers as mentioned in the paper. Due to the characteristic of our electrical input data, there was a need to handle noise and outliers. To address this, we applied dropout and legalization. After experimenting with values ranging from 0 to 1, we found that the best results were achieved with a dropout rate of 0.3 and an error legalizer values of 0.01. Since one of the labels, on-off ratio, has large exponential values, we took the log 10 of it. Additionally, we applied zero-score normalization to all labels. By changing the dropout, legalizer dense, activation function, and optimizer during training, we arrive at the best combination. The running rate was set to 0.001, the optimizer was a dumb, and 4 dense layers were used with the Lelo activation function. This shows loss and metrics during the DNN train process. Here's a more intuitive visualization of results. Orange lines represent the actual values, and the blue line represent the predicted values. While outliers still exist, mobility and threshold voltages are quite accurate. However, the S-slope does not fit the overall trend well, and the on-off ratio follows the trend but lacks detailed accuracy. Although the visualization showed improvements over the original settings, there were still slight differences in results. Now, let's revisit the paper's intent. The paper utilized DNN for analyzing 301 sets of gate voltages, drain current plots, considering the input data as sequential two-dimensional data. Typically, sequential data implies that previous data points influence on subsequential ones, such as stock price or weather patterns. However, in our case, the drain current values at different gate voltages are significantly independent of each other, even though this is sequential data. Since the x-axis values are listed at regular intervals 0.2 volt, we can also look the data as a one-dimensional sequence of y-axis values while maintaining the order. Therefore, we conclude that a one-dimensional convolutional neural network, 1D CNN, would be more accurate than a DNN. 1D CNNs are commonly used for time series data, strings, or audio analysis as they are suitable for smaller datasets and where maintaining order is crucial, which can prevent overfitting. Observing that these characteristics are suitable for our input data, we decide to replace the process with the 1D CNN. A 1D CNN processes sequential data by sliding convolutional filters over the input to extract local patterns, applying activation functions and pooling layers, flattening the pooled feature maps into a vector, and passing this vector through fully connected layers to produce the final output. We maintain the same normalization and legalization settings by adjusting hyperparameters such as the number of layers and learning rate. We proceed with training and found the most optimized combination which we applied. The running rate was set to 0.001, loss function was mean square error, the optimizer was a dumb, 4 convolutional layers with the Lelo activation function were used, without a dropout method, and zero-score normalization, and the L2 legalizer value of 0.001 were applied. This shows loss and metrics from our train process. Clearly they overlap well, and the gap between train error and value error is small. Let me show you the intuitive visualization of the ledgers. In the labels, plots are well distributed along diagonal lines rather than scattered randomly. Let's focus on the S-slope and on-off ratio, because others were already predicted quite accurately with our tuned DNN. Unlike the DNN, you will notice that the prediction and actual values closely align. They capture both the overall trend and finer details. Finally, let me tell you our conclusions. We confirmed that the 1D CNN produces better ledgers than the DNN in terms of time efficiency and usefulness for all 4 labels. Although the 1D CNN didn't preciously match all parameters values, it showed definite improvement. If we have more samples of higher grades than we do now, the ledgers would likely improve significantly. Thank you for listening.